Can you guys hear me now? Okay, good. So friction, there are two types of friction. One is static friction and the other one is kinetic friction. So static friction is the friction that keeps an object from slipping across a surface. So you have a big box, you apply force on the box doesn't move because there is this opposite force that is acting on the object that keeps it from slipping. Okay? And that opposite force is provided by the surface over which the box is resting. Okay? So that force is the friction force. And when the box is not moving, the friction is static friction. And the duration of friction, you see here this small f sub s, that's the static friction. It's opposite to the duration of the potential motion. Okay? So if there were no friction, the object would move to the right. Okay? But because of the friction, it's not moving. So that means this friction is opposing this force. So you again see the box is in static equilibrium. So the box exactly balances the force that is being applied to the box. So you see the free body diagram here. This is the push force. This is being balanced by this static friction. So you have this equal arrows. So this box is in state of static equilibrium. Now, static friction is not constant. Okay? It depends on how much force you provide on an object. So harder you push an object, the harder the friction force from the floor pushes back to keep it from sliding. So initially, you have a box, you apply a small force on that box. There would be a small friction force to oppose your force. And if you increase your force, the friction force would also be increased. Okay? Again, to compensate your force to keep it from sliding. So again, harder you push, more friction would be applied on the box. So that happens up to a certain point, okay? Certain maximum friction. So you increase the friction, there would be increase in you increase the force, there would be increase in the friction up to some maximum value. And once it crosses the maximum value, then it cannot withhold your force. Okay? So then the box will slip across the floor. So that maximum friction that the surface can exert on the object is equal to some constant times the normal force. Okay? So this constant is called coefficient of static friction. So this is the maximum friction that the surface can exert on this object. If you apply any force greater than this force, then the box will slide across the floor. It won't remain at rest. Okay? And this mu s depends on different kinds of object. Okay? It's different for different objects. I'll show you some values later. And this is the normal force. So we'll be using this formula a lot in solving the problems. Okay? So that's the static friction. And I already mentioned that. So just a summary, static friction is opposite to the direction along which the object tends to move. And Fs, or static friction, adjusts itself so that the net force is 0, so that the object doesn't move. And the magnitude of the static friction cannot exceed that, okay, this maximum value. You can only have up to this maximum value of the static friction. And if the friction force needed to keep the object stationary is greater than this value, then the object slips and starts to move. Okay, so let's look at this question. So we have a box on this rough surface, and you're pulling the box using a string or a rope. Okay, so the force on the box would be the tension of the rope, and the box is not moving. So in this situation, which one would be the correct expression? Static friction is greater than tension. Static friction is equal to tension. Static friction is less than tension. Static friction is equal to mu s mg, or there is no static friction. Which one would you choose? B? Yeah, that's right. Because the box is not moving, meaning it's at static equilibrium. So the condition for static equilibrium is the net force is 0. Okay, so you have this force and this force. Oh. So I don't know why it's. So this friction force and this tension must be equal to keep it at static equilibrium. So B is the right answer. Now there is another kind of friction force, which is kinetic friction. When the box is already moving, okay, then the force exerted by the surface is called the kinetic friction. And the kinetic friction is nearly constant. It's unlike the static friction. It doesn't adjust with the speed or the force. No matter how much force you apply, or no matter how fast the object is moving, kinetic friction is always constant. It's given by this formula. So just like in the static friction, we have this mu, but in this case, this mu is called coefficient of kinetic friction. Okay, in case of static friction, this coefficient is static coefficient. Okay, it's different from this one, and times normal force. So you see the difference. So in case of kinetic friction, it's mu k times n. In case of static friction, it's mu s times n. So if the object is in equilibrium, not static but dynamic equilibrium, what that means is if the velocity of this box is constant, then these two forces would be equal. Okay? Whenever you see this force is equal to this force and it's moving, it's already moving, then that means this V is constant. If these two forces are equal and the object is not moving, then V is 0. So you need to think about these two things. So V is 0 when Fs is equal to F push. See, someone is asking question. What was the answer to example on the previous slide? Didn't I answer that? Okay, so the answer is B for this one. Okay, this is static equilibrium. The box is not moving because the opposite forces are equal. Okay, so again, in the previous example, we have two forces equal and the box is not moving, velocity is 0. But here, we can have the box moving and still not equal to 0. It's moving with some velocity and still have the friction force is equal to the push force. Okay? So this case is called dynamic equilibrium. and this case is called static equilibrium. So there are two types of equilibrium. Now there's a third kind of case where we call it non-equilibrium. Non-equilibrium is when the two forces are not equal. So you will see one force is longer than the other. In that case, we'll have an acceleration. Okay, so you have this kinetic friction, and you have this force, push force. So one is longer than the other. In this case, it's not equilibrium. So you will have the net force. Net means push force minus F sub k would be mass times acceleration. Okay, they are not equal. So here are some of the values for static and kinetic friction. There is also third type of friction coefficient. We will not talk about that for now. We'll just leave that for the next time. So these are the values. Okay. Greater the value, more is the friction. So you see rubber on concrete has static friction of 1. Steel on steel has, if you slide steel over steel, the kinetic friction or the static friction would be 0.8. If you slide ice over ice, it's 0.01. It's very low friction. And kinetic friction is always less than static friction, okay? Because it doesn't take much force to keep the object from coming to rest if it is already moving, compared to starting the object from the rest. So kinetic friction is always less than static friction. So let's look at this question. A box with a weight of 100 Newton is at rest. It is then pulled by a 30 Newton horizontal force. Does the box move? If friction force, whether it's kinetic, if the static friction force is equal to the push force, then it's not moving. Okay, it won't move. If the two forces are not equal, then it's moving. Okay, so we need to see whether the friction force is greater than, equal to, or less than push force to decide that. So there is friction force here. So the maximum static friction is given by this formula. The friction force applied by the surface is coefficient of static friction times normal force. Okay. So in this case, the coefficient of static friction is this, given by 0.4. Okay. And then the normal force. So if you draw the free body diagram of the box, there is this normal force up and there is this weight down. And since the object is not accelerating up or down, so in this case, normal force must be equal to weight. Okay. Up and down forces are equal because it's not moving up or down, or it's in static equilibrium with respect to the vertical motion, vertical direction. So weight is mass times g, or in this case, it's 100 newtons. So that's 100 newtons normal force. So that's 40 Newton. So this is 40 Newton. Now you can decide whether the box would move or not. There's greater friction force. So that means the box won't move. Okay. So the maximum friction force is 40 Newton. The box can exert up to 40 Newton. You need to apply more than 40 newtons to move the box. Okay. If it is less than 40 newtons, if it is less than this maximum friction, then the box won't move. Okay, so the cause of friction is so the friction force in that instant is, let's go back. Yes, so in this instant, so yeah, you're right. I should have made clear here. So this is not the friction force at this instance. So this is the maximum friction force. Sorry for not clarifying that. So this is the maximum friction force. That's a very good point. So thanks for pointing that out. This is the force that this surface can exert, okay, at maximum. But at this instance, it's not moving. So for this instance, the static friction is only 30 Newton. Okay, so it would be equal to that. So make sure that the friction force here at this instance is not 40. 40 is the maximum it can go. Okay, does that make sense? It's not moving, right? That's why the friction force at this instance is 30 Newton. This gives us the maximum friction. Okay. So again, it's not moving. So in order to move that, you need to have your push force, this force, greater than 40 newtons, greater than that. So no matter how smooth an object looks in bulk or in macroscopic level, but at microscopic level, they are not smooth. They are not very smooth. They are very rough. Okay, if you look at this surface at microscopic level, you will see all these like tiny up and down. Okay, these high points and low points, and the cause of the friction is because of jamming of these high points and low points. Okay, they lock each other. Because of the locking, there is friction, and the amount of friction depends on how much the two surfaces are compressed. More the compression, more is the locking of this high point and lower point. Okay. Okay. Let's look at this question. So this box is already moving, and in this case, the box is speeding up. So you are pulling the box with a rope, and the box is speeding up, and suddenly the rope breaks. So what happens to the block? There is this kinetic friction applied on exerted on this block by the surface. Will it stop immediately, or continue with the speed it has when the rope broke? Continues speeding up for a short while, then slows and stops. Keeps its speed for a short while, then slows and stops, or slows steadily until it stops. So when the rope breaks, this one will be gone. There's no now force. There's no force on this side. The only force would be this one. So then, writing the Newton's second law, the net force would be F sub k is equal to total force is equal to mass times acceleration. So the acceleration would be F sub k over m. Okay. This is in the opposite direction. So you have this constant acceleration applied to the object. Constant acceleration means it will steadily stop until it steadily slow down until it stops. Okay. So the right answer for this one is E. Or you can say it slows down at constant rate, which is what we call steadily. Okay. Okay. So that's the friction. Let's talk a little bit about the sensation of weight. So we all feel the sensation of weight or heaviness or lightness. Where does that come from, the sensation? So the sensation of weight comes from the normal force, okay, exerted on us by the surface. So we are standing on, when we stand on a surface, what happens? So you have a surface and you're standing on it. So your body pushes the surface down because of the weight of your body, and in turn the surface will push your body up with the normal force. Okay. So there is this normal force up and this weight down. And when we are not moving, when we are at rest, this normal force and weight are equal. Okay. So this is the force that gives us the sensation of weight or heaviness or lightness or the feeling of our weight. Okay. And it is also called apparent weight. I don't know why I cannot write on PowerPoint. It's not allowing me to write properly. Sensation of weight, not water. Okay. So that means if the floor or surface provides higher normal force than our actual weight, then we'll feel heavier. Okay, we'll feel heavier when the force of the surface is greater than our actual weight. We'll feel lighter when the normal force or the force of the surface on our body is less than the actual weight. And we'll feel the normal weight, when the normal force exerted by the surface on our body is exactly equal to the weight of the body. Okay. So let's look at all these three cases, or one more case here. So we'll feel weightless when there is no normal force. Okay, normal force is 0. So the sensation comes from how much normal force you get. So this is when you are falling in sky, okay, and there is no surface that is providing you or giving you the opposite force, providing you the normal force. So this is example. The example for this one is free fall. So when you are falling freely, you feel weightless. Although you have weight, the gravity is pulling you down, but the apparent weight is 0 because there is no normal force. So let's look at all these three cases. So let me first show you one and then I will show you the other. So here, so we have this elevator connected to a rope. Okay, and this elevator is accelerating up. Okay? The direction of acceleration is up. So how many forces are acting on this person? So this person is the object of interest, which we denote by this dot. So how many forces are acting on this person? One is the normal force. Okay, so there is normal force on this person. Two is the weight of the object or gravity force. So those are the only two forces that are acting on the object or this person. Okay. Now let's write Newton's second law for this person. So Newton's second law is total force is equal to mass times acceleration. So what forces we have here? We have, using this notion, up is positive, down is negative. We have normal force pointing up, so it's positive, and then weight is pointing down, so it's negative. Okay, is equal to mass. Acceleration is pointing up, okay, so positive. So this is the force that gives us the sensation. Okay, so we want to know how much sensation we feel. So N is equal to weight plus ma. So I'm taking this weight to the right, it becomes plus. And we know weight is mass times acceleration due to gravity, and ma. So m and m are common to both the terms. So m g plus a. You see that our normal weight is mg, but the apparent weight is greater than that. So we have mg and this additional term. That means in this case the person will feel heavier than the normal weight, okay, because of this additional term that comes from this acceleration in upward direction. Now let's look at another case. Let me write it on that. So the second case is, let's say you have this elevator and person is standing on the elevator and there is a rope connected to that. So there is this tension of the rope, and now in this case the elevator is moving up but it's slowing down. Okay. Slowing down. Let me erase that for a second. So this is moving up, slowing down. So now you guys need to tell me which way would be the acceleration. I already discussed that a couple of times. When an object is moving up and it's slowing down, which way would be the acceleration? Opposite, yes, exactly. So slowing down will have v and a in opposite directions. If it is speeding up, v and a will have same direction. Okay, so v is up, it's moving up, so the acceleration will be down. So this is the case of moving up plus slowing down. So what kind of sensation will this person feel? So draw the free body diagram for this person. So there is this normal force acting on this person, and then there is weight. Okay. So normal force. So total force is equal to ma. Normal force upward, weight downward is equal to m. A is down, so we need to put minus sign here. So then sensation comes from this n, so n is equal to weight is mg minus ma. Okay. So you see the actual weight of the person is mg, but this normal force is less than mg because you have to subtract this thing from mg. So you get less than mg. That means n is less than the actual weight, meaning you will feel lighter. The person will feel lighter in this case when it's moving up and slowing down. Oops. So I would like you guys to think about this one. So I will let you guys think about this. I don't know why it's doing that. Let me just use a new page here. Okay, so think about a person is moving down and speeding up. So will the person feel lighter or heavier? Lighter. Okay. How do you know that? So yes, the acceleration would be down because velocity is down. Because it's speeding up, so acceleration also must be down. And free body diagram for the person is n is up, weight is down. So the total force is n minus w is equal to m minus a. So n is equal to mg, this is mg minus ma. Actual weight is mg, so this would be, you are subtracting this thing from actual weight. That means this should be less than the actual weight. So that means it will feel lighter. It's like riding a roller coaster. So when the roller coaster goes downhill, you feel lighter, right? Another case, a person is moving down and also slowing down. So in this case, what is the direction of the acceleration? Velocity is down. If it is slowing down, acceleration must be opposite to the velocity. Okay, that's the rule. So acceleration up. So normal force acting up on the person. Weight is down. So n minus w is equal to m. Acceleration up. We have the notion that up is positive, down is negative. So ma. N is equal to weight is mg plus ma. So normal weight is mg. You're adding this term on that, so that means n will be greater than w. So you feel heavier. Heavier, not heavy. Okay, that's that. What happens when this elevator is falling freely? Elevator falls freely. Free fall means when there is no acceleration. Yes, that's right. So the person will feel weightless because you have no normal force in this case. Okay, n would be 0. So when it's falling freely, you will see that the floor is barely touching the person. Okay, there is no normal force exerted on the person. So this n would be 0. So it's like if you have a pen or something and you drop it, your hand would be barely touching the pen, so your hand would not be applying any force. So it will be falling freely. Okay, so that's the normal force and sensation of weight. I think we are out of time. If you guys have any question, I can answer your question. Otherwise, that's all for today. Please take the quiz by the end of the day. And I will post some practice problems for the test. Please check the practice problems on Blackboard later this afternoon. And I have already posted the solution for the sample exam. So please check the solution and see if your solution is correct or not. And if you have any question, please feel free to email me, okay, about the exam or anything.